this is Dr. Mad. Yeah, I know, it's me again. Okay, now let's see the implications of the, Lorentz formulas. We've seen that, the conclusions that we can draw from those equations were threefold. First there was relativity of space, because, depending from where you do measurements of distances, for instance, you get different results, based on these values here. Same thing for time using this particular equation here. And finally, there is a speed limit, apparently, due to the gamma factor here that we're going to use in the equations of special relativity. Now, based on this equation, let's see some concrete examples and values we can get that we can use later to solve the mysteries, that we talked about before. Okay, here let's assume, we have the ground here, which is fixed, and the car moving like this, with a constant linear speed. Well, what the relativity says is that we can also consider that it's actually the ground here, or the Earth, if you want to call it that way, that's moving relative to the car. And you can, being in the car here, you can consider that the ground is moving this way and you're stationary, So what we want to do is to measure, the distance viewed from the ground here, A prime, B prime, and compare it to the distance viewed by the car here, call it AB, for the same points on the ground. So which look, in the previous to before relativity would be the same. B would be equal to B prime, and A would be equal to A prime. Now, okay, yeah, that's what I said. So in order to know the distance, we can say, A prime, B prime is equal to B prime minus A prime, if F prime is the frame of reference on Earth, And then we apply this equation here, and we say, well, B prime minus A prime would be equal to, B prime is gamma times B minus VT, minus A prime, which is gamma times A minus VT, okay? And therefore, we can easily see that B minus A is equal to 1 over gamma times B prime minus A prime. And what that says is that the distance on Earth, the distance of these 2 points who are fixed on Earth, well, they look smaller when you look at them from the car, from the moving frame of reference here. Okay, and the way, the factor by which they look smaller is 1 over gamma. Gamma is always greater than 1. Therefore, the distance viewed by the car is always smaller than the distance viewed from Earth. Okay, now let's do the same thing for time. Okay, so let's assume that we have the car moving here, and we want to measure, a unit period of time. So we'll start from t primes equals 0 viewed from the car, and add at t primes equal 1 again viewed from the car. So it will be, something like this with 1 now here. And the frame of reference will be the car. Therefore, we can use, the same frame of reference here with x prime equals 0. Okay. So what we do is at x prime equals 0 and t prime equals 0 here, we start the clock, and when we arrive here, we still have x prime is equal to 0, but now we have t prime equal 1. And now we try to see what are the values of the time here viewed from Earth, from the ground. So since we have x prime is equal to 0, we can pick, again, to simplify things, t prime is equal to 0, and from that we get x is equal to vt, because gamma is non-zero. And therefore, we also have gamma t times 1 minus v squared over c squared is equal to 0, because of this now. And assuming, again, that t prime is equal to 0. Therefore, that means that t is equal to 0, which is no surprise, okay? But now, what's more interesting is when we reach that point here in time and see what's its value here is from Earth. Now again, x prime is equal to 0 because, the frame of reference relative to the car didn't change. But now we have t prime is equal to 1. Therefore, this value here is now equal to 1 here. And from that, you can derive that 1 over gamma times t is equal to 1. Okay? Therefore, t is equal to gamma. And what that means here, based on this, is that clock ticks last longer, in the car than on Earth. And therefore, the time runs slower in the car. So when you're moving, times is slower. And again, with this magic factor, the Lorentz factor called gamma. So that's for duration. Okay, but there's another concept related to time, which is quite often overlooked and forgotten due to relativity. It's a concept of simultaneity. Okay, and of course, simultaneity is also a relative concept. Now, let's see how Einstein showed us this. He said, well, first of all, we need to define what simultaneity is. This is something, it seems obvious, but it's actually not obvious, as you will see, because it has a lot of weird implications. So he said, how can we define simultaneity? Well, for instance, if I have some event coming here, and that's sent to me at a certain speed, like speed of light, for instance, and another one coming here at the speed of light, then if I see both of them here at the same time, then I will say these events are simultaneous. Okay, so that sounds pretty good. I mean, you can use other definition if you want to, but this one sounds good to me. So if you get two lightnings here, if you can view them here as one single lightning, well, you can say, okay, this space event here was simultaneous to this space event here. Of course, relative to this frame of reference, which is a Galilean frame of reference, no acceleration, blah, 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 blah. Okay? Okay. So now that we have defined simultaneity, and I hope you like it, then we can go further. Now let's assume that instead of being, standing still here, we're in the car moving, in this direction there. What will happen, okay, for the same two lightnings which were simultaneous when viewed from Earth? Well, what will happen is that we'll see first this lightning here because the car moved like this, and therefore the distance here, was shorter than the initial distance there. And then we will see the lightning coming from there because it had to go through a longer distance there. Therefore, relatively to the car here, these two events are not simultaneous. Yeah, sorry. I mean, you accepted the definition before, so you can't change it now. Okay? Yeah. Now, that means that simultaneity depends on frame of reference. Yes. Now, let's see in more concrete terms what happens. Well, first of all, we get two clocks here, which are, clocks on Earth. Okay? And let's assume they are synchronized. Okay? So they show exactly the same time. And they show simultaneous times, if you wish. Okay? Okay. Now, let's assume that we want to look at those watches here, those clocks, from the car, which is moving, from this direction here, sense rather. Now, what we get according to the Lorentz formulas is this, right? And that, for t prime b and t prime a. And from that we can derive that t prime b minus t prime a is equal to gamma times minus vc squared times xb minus xa, being the places which are on Earth, where the two clocks are sitting. And from that, my friend, we can say t prime b is equal to this value here, which in turn is equal to t prime a plus v over c squared times ab, which means that this clock is ahead of this clock viewed from the car here. They're not in sync anymore, so that means that when you have two clocks in sync like this on a steel frame, well, if you're in a moving frame, one will be ahead of the other. Yes. And remember that, because that's key to understand the twins paradox that we're going to see in a few minutes or in another video. So, considering time, time relativity, we have two things to remember. One, clocks do not tick at the same rate, and two, thank you, sync clocks do not display the same time, depending on the frame of reference you're using. Of course, when you have frames of reference moving in a linear constant speed. So that's something we're going to need to remember when we look at the twins paradox, for instance, in a future video.